we're rolling. Any questions?
The master set's due today, correct?
Correct.
Do you want it in person or uploaded through Blackboard?
Yes.
Okay.
So, either way, personally, screw the environment, let's just kill the trees. No, I prefer grading on paper, but I also understand it's not necessarily realistic, that some people are not necessarily ready to hand it in right now, but will be ready at midnight. So, either way. Just if you're submitting it online, please pay attention to the naming convention that is posted in the syllabus. I have made some changes for those who had me in 151 2 weeks ago. I want it submitted as a single document. Before I allowed multiple pages and multiple documents, but I really want it as one document. Any questions? Any other questions? I'm glad the master set went that well. Excellent. Because I hate to think that that all of you waited till the last moment to do it. All right, so officially the class is completely online and the lab is during this time, but we're not going to do a lab today. We're going to sort of go over material. Slight correction. If you go into the Blackboard site under labs, you'll see that there is one that I posted. It is not an experiment. It is a series of conceptual questions related to the electric field and the electric force. So that is due in a week. I think that pretty much sums it up. So this week we're supposed to be dealing with chapter 19, but let's sort of drop back just a little bit and talk a little bit about electric field. It is a vector. So what is an electric field? I'll take equation or concept.
Coulomb's constant times charge sub 1 times charge sub 2 reducible.
The use of two,
Q sub 2 third is 1.
is there one?
Depends, is this the electric
Field.
on 1 from 2?
You're like, all right, so you're thinking of electric force. So let's just go ahead and turn that into an F. So KE, Q sub 1, so we'll do the force on 1 from 2. You want to finish it up?
Divided by distance between the bar squared. R sub 2
All right, so that's the electric force that was discussed sometime last week. Yes, last Tuesday. All right, then I'll pose the question. You've seen the video, presumably you know the answer. I have a charge Q1 sitting here in the universe. All I've got is this one charge. It's sitting there, fat, dumb, and happy, sort of basking in the glow of nothing. I put a second charge in here that is the same sign as that one. What's gonna happen?
There we go.
Okay? How do they know the other one is there?
You don't.
Then how do they know to be repelled?
You assume there's some sort of field that's either charges or sensing from the other and they don't like it, so it's like the other one.
Okay, so in essence, that's the electric field. So it's assumed that that each is giving off some sort of field, as she said, and in the video and in past lectures, I've sometimes referred to it as electric pheromones, but I'm the only one who would refer to it as that. So if this is giving off something that the other one is going to sense, it must exist even before the second one shows up. So if this is a positive charge, then it gives off an electric field. So that the difference between the force and one difference between the force and the electric field is that the electric field only depends on a single charge. So, which was my hesitation when Olivia was talking about the electric field earlier. My electrostatic constant times Q. There's only one charge involved here. So if we're talking about this particular charge, since I have it labeled as Q1, this would be E1 is equal to KE Q1 R squared R1 hat. And as mentioned in the videos, when they came up with this, they had no idea if this was real or not. But later on discovered that there was some legitimacy to it, which is why it's still in the textbooks. So we're talking 19th century. So when I put a second charge here, it senses the electric field and it reacts to it. So the force on 2 from 1, and it is the reverse of that, the force on 2 from 1 is going to be just the electric field from 1 times the charge of 2. So the electric field is going to have the same sign as the charge. So if the electric field is negative, then it's in the negative R1 hat direction. So that means R hat direction is away from the center. Negative would be towards the center. So if if Q is negative, the electric field is pointing towards the charge. If it's positive, it's pointing away from the charge. And so Q2 has no idea that this is here. All it does is sense that there's an electric field there and will react to it, regardless of the source. This will give us a very nice advantage later, because we don't have to really talk about the charges at some point. We can just talk about the electric field and assume that the charges are configured to create it. All right. So if I have an electric field pointing this direction, and I put an electron right there, which way will the electron go? Which way will it be forced? I saw one finger pointing in a direction. I've seen a second finger pointing in the opposite direction. Oh, you changed your mind? All right, 2 fingers pointing in the same direction.
I think it's away. Well, away. Well, towards.
that way. So I've gotten 3 fingers pointing this direction, and 4, anyone want to go this direction? What creates an electric field going to the right?
Negative charge,
Where?
at the source, so it would be to the left of it.
So a negative charge over here.
Yeah,
If we go back to the formula here, if Q is negative, so let's say it's an electron, so I have the electric field from an electron would be the electrostatic constant times negative E over R squared R hat, which means that the electric field of a negative charge, the magnitude is KE times the charge of an electron over R squared, and the direction is negative R hat. Negative R hat towards the center. So if it's a negative charge, the electric field's pointing towards it. So if the electron were here, the arrow would point towards it, so the arrow would point that way. As such, there could be a negative charge over here. What else could create an electric field going that way?
Positive charge
Where?
to the left of the electron.
All right, so I could have a positive charge there. And the third option?
Positive and negative.
Okay. In each of these cases, the electron, if that's the negative charge over there, the electron would get repelled. If it's a positive charge here, it would be attracted. And if you have both, it's going to be repelled and attracted. But in each case, the electron's going to be forced to the left. So we have our rule that negative charges flow upstream or flow opposite the electric field. I'm going to put external there. It's supposed to be understood that an external electric field, the electron is not affected by its own electric field. That we know of. What would happen if an electron is affected by its own electric field? Why does that contradict stuff that we've learned before? So an electron creates an electric field. If it influences the electron, then I could have an empty universe, I stick an electron in there. What would happen to the electron if it was influenced by its own electric field?
It would stay still.
Why would it stay still?
Well, like all of its force is going inward. Or I guess its electric field is going inward.
The electric field is going inward, but if it's affected by itself, if it doesn't move, then is it affected? Therefore, if it is affected by its electric field, what would happen to it?
It would always be moving.
So, that would violate Newton's third law. It exerts a force on itself, and the opposite force would be what? So, it's not affected by itself. It has to be affected by an external electric field. The electric field are vectors. I'm hoping that you know how to add vectors. If not, in the lab that we will do on Thursday, that will set up a problem for you to add electric fields. please know how to add electric fields. Because I can pretty much guarantee on the first test, there'll be something about adding electric fields. Alright, so the rest is just basically plug and chug for the most part. So if I have a positive charge here and a negative charge here, I have electric field lines that are going away from the positive charge. I have electric field lines going towards the negative charge. And so with these two competing electric fields, if I have a spot, say right here, I have an electric field going up and to the right. I have an electric field coming down and to the left, no, down and to the right also. The total electric field here is the sum of these electric fields, thus the adding vectors. And so if we map out exactly the total electric field here, well, there'd be one that's going straight this way. And then ultimately it would just sort of curve like that. And you draw it until you get tired of drawing lines. I find it helpful to think about that the positive charges are like a fountain spewing water up, and the negative charges are like a drain, and that's where it ultimately goes. So this spews water up in all directions, but ultimately it gets drained into there. So we can now look at more sophisticated versions. We'll make that positive and that negative. And the electric field lines are becoming off of the positive and into the negative, except it's not a point charge anymore. It's not, we don't have the spherical symmetry. But what it turns out is the electric field lines will be coming off this thing perpendicular to the surface. And at the corners, and then ultimately all goes into this drain over here. So these would sort of curve inwards, and these would curve more, etc. Questions here? So one of the rules of electric fields is that they were going to be coming off perpendicular to the surface. As a matter of fact, if I take let's say I have a conductor here, and it's neutral. It starts out as neutral. I now take a whole bunch of electrons and I throw the electrons onto it. So put a bunch of electrons here. What's going to happen to the electrons?
They're gonna spread out.
I heard.
I said they were gonna spread out.
Okay, and you said?
They'll get to the surface.
Okay, both. So they will spread out because they hate each other and they want to get away from each other as much as possible. But they will start to spread out on the surface. That's supposed to be on the surface coming out, but it's probably not drawn particularly well that way. Now, as they're pushing each other out, basically, if I stuck an electron here in the middle, if there's an electric field in the middle, that this charge right here would then get pushed. If there's no electric field in the middle, that the electron would not get pushed. They will move until the electric field in the middle is 0. So for a conductor, the electric field is 0 inside. not at surface. So they'll spread out to the surface, and then they will concentrate in certain areas. So if I had a square conductor, I know if I throw excess charges onto it, it will spread out over the surface. Where will they congregate?
Corner.
Yes. So the tighter the radius, the more you get here. And again, if you haven't watched the video, watch the video. And I'm not saying there's not any in here, there are some all over the surface, just higher concentration here. All right, now let's get to the chapter 19 stuff. I just want to hit some of the basics there again in the videos. I know that the force, and I'm going, no, let's go with the formality of it. KE, Q1, Q2, R squared, R2 max. Let's parallel that with the force due to gravity. Oh, that is the electric force. I should have a subscript E down here. That's a G. From 151, what is the general formula for the force due to gravity?
FMG? Wait, is it F equals mg?
That is a specific case that, well, you could use that as a generalized case if you know what little g is, but that's not what I'm looking for. I'm looking for the other formula.
Is it just like this one, right? It's like, K, well, is it K or is it M1, M2 over?
All right, M1, M2 over
I don't remember. Oh, R.
R squared. The thing in front is a big G. It's the gravitational constant